Okay, we are now recording. So I'd like for everyone to start by going to the Jamboard that I sent in the chat. And we'll start going, there's 2 pages to this Jamboard. So we'll start on this first blue page. Just to double check, can everyone see my screen? You can just let me know in the chat if you can. Yes, you can. Fantastic, thank you. Okay. So here we've got a set of parallel plate, parallel charged plates, or capacitors, if you want to call it that, and we have point charges in between them. The yellow lines, or I guess the yellow arrows, are indicating the electric field. And so the plates and the parallel plates are the same for each of the 6 cases that I've given you here, just labeled A, B, C, D, E, and F. And we have the same 2 charges in each of these different systems, and they're just positioned differently. And so what I want you to do for this first Jamboard slide here is take a sticky note, and if you haven't used Jamboard before, off to the side, click a sticky note, type whatever, and save. You can make it different colors, all that fun stuff. And on a sticky note, I want you to rank the electric potential energies of the system, and we're defining the system of consisting only of the 2 point charges. So for a system of just 2 point charges, the green and the pink, just rank the potential energies just in order. We'll say smallest to biggest so that everyone's consistent. And I'll add that in the description here. So from smallest to biggest. So I'll mute myself for a couple minutes and give you some time to do that. Once you're done, I'll give you a ready to continue message in the chat, so you can let me know when you're ready to have a discussion about this. Or I guess when I see 3 sticky notes, that'll be a pretty good indication as well. And if you have any questions, let me know. And that includes questions about the setup and the physics here, or also questions about what I'm asking you to. Okay, looks like we're ready to continue. So I see everyone agrees on the ranking. And so what we're seeing is that F, this bottom right one, has the smallest electric potential energy, and it should be small because you have two opposite charges very close together. That's what they want to do. So that's I know that's where they want to go. They're attracted to each other, and so yeah, since they're close together, there wouldn't be a lot of potential energy to that could be used to make them move somewhere else. We have D as the second smallest. So, yep, the charges are also very close together. D and F could almost be the same. I guess maybe technically the two charges in D are a little bit further apart, but not considering the external electric field. Yeah, those two have very small potential energies of the system. Next, we're saying B, okay, which are more spaced out. They're on kind of opposite sides of the parallel plates. And then A, which are further, a little bit further still. And then C, which are further still. And E. Okay, yeah, looks good. So pretty much the electric field is just, not the electric field, goodness, the electric potential energy is just dictated by how far apart these opposite charges are, what their separation is. Okay, well, that one went really well. Let's go on to the second slide, where, as I'm sure you could have guessed, we're now going to include the parallel plates in our system and include that external yellow field shown with the yellow arrows there. So, yeah, I'll give you a few minutes to do the same type of thing. Rank their potential energies now, including the external electric field caused by these plates. And just one thing is that we'll treat these parallel plates as infinitely big, so you don't have to worry about. Well, yeah, that's a nice approximation we'll make. You don't have to worry about any weird things happening with the electric field around the edges of the plates or anything like that. So I'll give you a couple minutes and another ready to continue message. And yeah, rank these potential energies again, we'll say from smallest to biggest. Okay, it looks like we're ready to talk about this one. So everyone's got C as the smallest. Oh, interesting. So everyone has C, B, D, F, A, E. But one person is saying that C actually has the biggest potential energy and the system E has the smallest, whereas the other two people have that flipped and they're saying that no, C actually has the smallest potential energy and the system E has the biggest. So if you said that C, the system C, has the biggest, largest amount of potential energy, can you tell me why? You can write out in the chat or say out loud, whichever you prefer. And if you said that no, actually it's system E that has the biggest, why does system E have the biggest amount of potential energy?
Yeah, I got my signs backwards there, I think.
Okay, so we all agree that C has the smallest amount of potential energy then?
I think so. I think that's what we've seen here.
Okay. So let's take a look at this then. So we're saying that, well, for C, we have the green point charge, which is the negative point charge. And you can tell that because the electric field lines between the plates are going towards the green plate. So, well, and we're using the convention that electric field lines go from positive to negative. So the negative charge is right close to the positively charged plate. That's good. That's what it wants to do. And also, the positive charge is close to the negative plate. Okay, nice. That's also what it wants to do. There is something about the configuration of the system that does give it an amount of potential energy, not a negligible amount of potential energy, and it's that the green point charge and the pink point charge, or the negative and positives, they're not very close. So if you were to place these point charges in the capacitor where you see them in system, I almost said number C, in system C, and you to just place these charged particles there and let them go. If the potential energy of this whole system was really low, then they would pretty much just stay there. Or maybe they would have a really small force acting on them and a small acceleration, but they wouldn't move very much. However, the point charges can still interact with each other, and they're going to attract each other, right? So this system would actually have quite a significant potential energy between these point charges, because this potential energy would it's a good way of explaining it. I guess you'd say that if you were to place these charges in the capacitor here and let them go, they wouldn't just sit there. What would happen is that the green charge would move down, like down on the screen. The pink charge would move up on the screen so that these point charges could be closer together. And if they were to move that way, that means that they would have some kinetic energy, because they're moving towards each other. Where did that kinetic energy come from? That means there had to have been a significant amount of potential energy in the system to begin with. So C actually has quite a large amount of potential energy for that reason, because the separation between these two oppositely charged, like point charges, would want to bring them closer together. To contrast, something like in part or system D here, the negative point charge is close to the positive plate, and same, well, but opposite goes to the positive point charge. And so if you were to put these charges in this position here between the plates, they'd probably just sit there, because the green charge would be equally, maybe not exactly equally, but approximately balanced out by the positive plate and the positive point charge. And same goes for the pink charge as well. If you were to put them there, they wouldn't really move. They wouldn't gain any kinetic energy. And if they're not going to gain kinetic energy, then there wasn't any potential energy to begin with. I will say one thing, that E definitely has very small, well, and practically zero potential energy, because there's no electric field outside parallel plates. So E should have the smallest amount of potential energy, because there's just point charges just sitting there in space, pretty much isolated from each other, and in not like in no external electric field or anything like that. So with that in mind, if you have questions, put them in the chat. If not, look through your answers again and kind of use that reasoning about the potential energy. See, like if you were to put these particles in the configuration that they're in for one of these systems, what would they do? Try thinking about it that way. If you have questions, let me know. Otherwise, I'll give you another ready to continue message once you kind of thought through it again, and we'll go from there. Okay, question in the chat says, wouldn't the plates in E repel the charges outwards? Okay, like yes, but actually no. I totally get what you're saying. So for system E, you'd have this negatively charged plate, and there's a negatively charged particle right beside it. And same goes for the positively charged plate and particle. And you think, like intuitively, it makes so much sense that these charged plates would repel the charged particles. But if you remember when we were learning about capacitors and charged plates in the parallel charged plates in the first place, we said that, well, the electric field due to a charged plate is uniform. And we're assuming our charged plates here, our capacitor here is infinite, so we don't have to worry about any weird things happening around the edges. And so using that assumption, anywhere outside of the two charged plates, you would have like a negative electric field from the negative plate, but you'd also have a positive electric field from the positive plate. And so outside of the plates, those electric fields would cancel. Another way you can think about it, I'm not sure how much you've looked at inducing charges. I honestly don't remember how much of that was covered in this class yet. But I guess another way you could think about it is that all of the positive charges in the pink plate are going to be attracted to the green plate. So they're all going to be on the inside of the pink plate. So there wouldn't be an electric field overall kind of outside of that plate. And same goes for the green. So on this green plate, all of the charges here would be attracted to the pink plate, and so they'd be lined up all on the inside. And so that's what causes the electric field between the plates. But outside of the plates, again, assuming that they're infinitely big and all those things that makes the physics nice, there's no electric field outside of the oppositely charged parallel plates. Does that clear that one up? Is there? Yes? Okay, fantastic. So let me know when you're ready for me to, I don't know, like talk through the answer for this question, I guess. Okay, looks like we're ready to go on. So, what have we got for a ranking now? So, everyone's saying that A is the biggest. I agree, A is going to be pretty big. C is, I mean, okay, before I say anything more, I'm probably going to forget what I'm saying while I say it, so I'm going to write as I go. You might not see what I'm writing your own uh, on your own Jamboard because it won't show it until I click out of the text box. But I'm sharing my screen, so if you want to watch what I'm saying or just listen, I mean, it's up to you. So we all agree that A is pretty big. Okay. Um. Okay, and then after A, we have that F is pretty big. We also have C. Um. Oh, and we have someone has changed their sticky note. Okay, A, then we're saying A, then F, and then we're saying A, then C. Okay, so for F, let's see, what would the charges have to do to get to where they want, get to what would make them happy? So for F, this green charge would just kind of go around the pink one a little bit and line itself up closer to the positively charged plate, to that pink plate, and the pink positive charge would kind of come over to the right and down a bit, and they'd end up lining themselves up just like they're lined up in D, actually. So these two charges actually wouldn't have to move very much. They'd have to rotate a little bit, but they wouldn't have to move too much. So they wouldn't gain a whole lot of kinetic energy in doing that, which means that they wouldn't have that much potential energy in the first place. Still a significant amount, definitely more potential energy than the system would have for the configuration in D, for example, but there still would be some. Let's look at C by comparison. So system C has a positive charge. It's close to the negative plate. So that's nice. That's what it wants to do. And it's also, but it's quite far away from the negative point charge. And now to find exactly how much work would have to be done for it to go closer to the point charge, and same thing, the green charge would come down closer to it, to look like the configuration in D. We'd have to know the magnitudes of the charges, the strength of the electric field, things like that, to see exactly how much work would be done on the particles for them to move that way, or how much kinetic energy they would gain in doing so. But that big separation between these opposite particles, these oppositely charged particles, I should say, that big separation would make a significant potential energy for this system. So based on that idea, kind of looking at the distances between the charges, say that the system, I'm doing this kind of backwards in my typing, but C would probably have the kind of the second biggest potential energy. And this is approximate with numbers or ratios of the, like comparing the electric field strength, comparing that to the electric fields from the charges, things like that. You could find this out a bit more conclusively. I don't know if that's a word. But yeah, the big separation between these two opposite charges would cause this system to have quite a bit of potential energy. F would, so I think that F, okay, so we have F has a lot of potential energy in the sticky notes here, but also B is ranked fairly high. F and B, again, you'd need more information to know for sure. They are pretty close. So I'd say the particles would probably have to move a bit further for the system F. So the system F might have a slightly bigger potential energy than B. But those two do look kind of similar. Next, we have, well, let's see. Everyone agrees that E is the smallest because there's no potential energy in that system. And so I guess that leaves us with, who are we missing? D. Ha, we're missing D. And everyone agrees that D should be fairly small. I guess the yellow sticky note has D ranked as about middle. But D should be quite small because the green and pink charges, those oppositely charged particles, they're close to each other. They're also pretty close to the oppositely charged plates, and that's where they want to be. So I would put D as our second to smallest potential energy. Because apart from being outside the plates and being in no electric field at all, the configuration in D is about as happy as these particles are going to get. Okay. Are there any questions about this? Let me know in the chat. If you don't have a question, you can let me know that you're all good, and we'll go to the next thing. And while you type, I'm going to eat a jelly bean. You're eating mini eggs? Nice. Nice. All right, I'm glad that helped to clear a lot of things up. Okay. So that's it for this Jamboard. Let's move over to Gaussian surfaces, Google Draw. That's what it's called. Okay. So here we have some diagrams. So this is just to get you thinking about using Gauss's law, about flux, things like that. So we have 3 different systems, and there's 3 of each of them. So that's for each of you. I'm just going to double check how many people are in this meeting so that everyone gets a set of diagrams themselves. Okay, perfect. So before we get into any details, can everyone click on one of the green circles and make sure you click on one that no one else has clicked on? Perfect. That is your system, and you can have that row. Now we're not fighting over each other's charged objects. Okay. So, yes, that is all yours, Anonymous Kraken. You are right. Okay. So for each of these systems, what I want you to do is add to your diagram a Gaussian surface, an imaginary surface, is what I like to call them, that would allow you to calculate the electric field. And I've given you the regions. So these, not that. These 3 descriptions up here, that's where I want you to calculate the electric field for each of the 3 systems. And so you can go in here to shapes. You can make a circle or a triangle or a square or a cylinder or a sun, apparently, if that's what you want your Gaussian surface to look like. So add a Gaussian surface for each of these. I do want to point out that when you do a triangle, for example, you can make the inside of your triangle transparent so that it's just like the black line, if that would be easier. Okay, so yes, add a Gaussian surface to each of these, and it should be a convenient Gaussian surface that would let you calculate the electric field in the region I've described. Once you've done that, I also want you to type, and actually when you make an object, you can, or like a shape, so here's a oval, for example, you can double click on it and actually like type stuff inside. And I just want you to write out how much charge would be enclosed in your Gaussian surface. And it's annoying typing the Greek letters, so you can just type out like RHO for rho, and oops, this should also be rho. And same goes for like lambda and sigma and things like that. So that is your task. If you have questions about it, let me know. In the meantime, I'm going to mute myself. You're ready to continue, message, and let me know how it goes. I do want to point out one more thing. I'm sorry. I said I was going to stop talking at you, and here we are. Lambda, sigma, and rho are charge densities. Charge per unit length, charge per unit area, charge per unit volume. Those are not an amount of charge in and of themselves. So what I want you to figure out is how much actual charge would be contained in your Gaussian surface. Okay, I'll shut up for real this time. And just to clarify, I want you to let me know when you're ready to continue once you've just done the first system, like the solid charged sphere, so we can talk about it and any like mistakes or anything you can fix for the next one. So yeah, let me know when you're ready to continue, like once you're done just with the charged sphere. Oh, wow, that was fast. Okay, perfect. So we're looking to calculate the electric field inside the charged sphere. So if the region that you're wanting to calculate is within the sphere, so it's uniformly charged inside, you want to calculate the electric field at some distance from the center of the sphere, inside the sphere though. So since you're calculating a distance inside the sphere, your Gaussian surface should also be inside the sphere. It should be in that same region. I'm just looking to see, can I make check marks on this? It's looking like I can't. Well, I'll just say it in words, I guess. This second system here, that looks really good. You've got your Gaussian sphere. I think it's supposed to be a sphere. And it's inside the charged sphere. So that would allow you to calculate, calculate the electric field inside. The top row system has, the top row system has a Gaussian surface inside, and so the bottom row person would have to make their Gaussian surface inside the sphere as well. So now for as to how much charge is inside, I think I'll open a Word document to type it out, because that'll be easier than trying to understand me writing it in the Google Draw. So rho, the density rho for the charge is equal to the charge of the total sphere divided by the volume of the total sphere. If you want to know the charge enclosed, so we'll call that Q sub enclosed, that will be equal to the charge density, because that's a constant for no matter what piece of this object you're looking at. You'll have the charged density multiplied by the volume, but it's the volume of your Gaussian surface, because you want to know the electric field at that surface. So the charge inside will be how much charge is inside specifically that volume of the Gaussian surface, or the imaginary shape. So the charge enclosed will be rho multiplied by V of the Gaussian surface. I think I'm going to get rid of this times symbol. You know those are multiplied. And also an X like that can sometimes stand for a cross product, which is not what we're doing here. So we'll just, yeah, I'm just going to write it like that. So the enclosed charge is that rho divided, or sorry, multiplied by the volume of the Gaussian surface, right? And I say multiplied because in this first equation, you'd get the charge, like isolate the charge by multiplying the volume to both sides. So then, I guess lastly, I can just plug in what we have. I mean, I guess it would depend on what exactly you're given in the question. You could leave it as rho if I just gave you rho. So I guess for this question, just leave it as rho. If instead they gave you like the radius of the sphere and the total charge of the sphere, then you could calculate the charge density for yourself. In this case, though, I just gave you rho, so we'll do that. And the volume of the Gaussian surface, that would be our 4 pi. Oh, that should be 4/3. I hope you understand what I'm trying to do here. There we go. So the 4/3 pi r cubed, that's the volume of the Gaussian surface. And I'm specifying it this way just because this little r is like the variable that we would use for the Gaussian surface, or to describe it. So that would be our charge enclosed. Okay, nice. And for those of you who have just put volume, as long as you know, and on a test question that you indicate that it's the volume of a Gaussian surface, if the question doesn't ask you to do anything more than that, just make sure you do make it clear that it's the volume of the Gaussian surface and not of the charged sphere. Okay, we've got about 10 minutes left, and I think of the two examples, the two last examples, the third one's probably going to be the most challenging. So let's do that. So let's do the cylinder one now. So we have a cylindrical shell outside of a charged, like a charged rod or a charged wire. And so the shell has a surface charge density, and the rod has a linear charge density, just because of the different geometry of the two objects. So I want you to do the same thing. Draw or place or whatever a Gaussian surface that you could use to calculate the electric field outside of both the rod and the shell. And then tell me what the total charge enclosed is. And that should pretty much wrap it up for this PAL session. Not to be super obnoxious, but can we make our Gaussian surfaces a color that is not the same as the charged cylinder? Like I know you just like copied and pasted, but ooh, yeah, it just makes it easier to see. We appreciate it. I know you're still writing. Take your time. I just want to point out to the owner of the green Gaussian surface that you have a charge equal to two charge densities, and those aren't quite the same quantities. They're definitely related, but a charge density, no matter what, like even if you add it to another charge density, can't be equal to a charge on its own. So just a little heads up there. Take your time and give my message a thumbs up when you're ready to keep going. Okay, I see that some of you are still working, and I'm sorry to interrupt, but it is almost 7 o'clock. I think what I'll do is that I see some good thinking and reasoning through and working stuff out here, and I don't want to ruin the joy of coming to the answer on your own. I don't want to ruin that for you. So here's what I'll do. I'm going to leave this question with you, and you can keep working on it. You can ignore it and pretend it never existed for tonight. Up to you. And tomorrow's PAL session, I think I'll start by doing a worked example, like an actual problem with like numbers and things like that. And I'll do it for this system so that you can kind of get your answer there. If you can't come to tomorrow's PAL session, I'll give everyone in this meeting access to the recording right away. So by about 7:30 tomorrow, you should be able to see it on your Microsoft stream. Um, and so I'll send a link in this same chat from today to tomorrow's recording if you need it. Your brain is a bit mush, mine too. Oh, honestly, same. So yeah, I think I'll leave this with you for tonight and we'll go over it. We'll start with a question similar to this in tomorrow's PAL session. Um, And you can either come to the PAL session and see it there, or I'll definitely give you all access to the recording as well. So we'll wrap that up there for tonight's PAL session, and we'll do I'll stop the recording first and stop sharing my screen and all that fun stuff.